Yep. Hello. Yeah. Okay, is it working?
Just a second. Yes, we can see a slide about sparsity and vector distance. Okay, great. So it is my pleasure to announce our next speaker, Corbinian Schlosser, who is going to speak about sparse structures for the Koopman and Perron-Frobenius operator. Please go ahead.
Thank you, Jochen. Hello. The pleasure is also very much on my side. I'm very happy that I get the opportunity to present this year again a little bit. And this is about work with my supervisor, Milan Korda. And yeah, it was a little bit motivated by applications and data. So I put a picture here, which is a social network graph. And here you can see there are many different substructures that can or should be exploited. And yeah, we'll be looking at one of them, which we refer to as sparse structures. So, what is the rough idea? This should be illustrated here a little bit. So we have a dynamic system on a large set up here, where the flow is denoted by phi. And the idea now is that we can find several smaller subsystems where we transfer them, to which we can transfer via some projection maps down here. So that instead of looking at the whole system, we want to look at some smaller systems here and investigate the global system from these smaller parts here. And very classical examples are when our system up here is just a product of these systems, for example, but we want to generalize this a little bit further. So our setting here, we want to work with the Koopman or the Perron-Frobenius operator. So we have to define our dynamic system. So that means we have a set X and equipped with a semi-flow on X. So this is a family of functions that satisfy the semi-flow property here. And now the idea of Koopman theory, we've seen this before today as well. So thanks for the speakers before. So is the following. So here we have our original dynamic system, but we don't have any linear structure here at all. We just talk about a set and semi-flow. But down here, we want to transfer this system up here to a system down here where we have some linear structure. So that means we talk about V, which is a vector space here, and T should form a semi-group of linear operators. And at first, when I saw this, I was surprised that this is even possible. And then I was even more surprised that this works in such a beautiful way. Namely, as we've seen before, we can just define a very good candidate for this function, for this operator T here, namely the Koopman operator, just by composing, as we've seen before today. And this then leads to this following guiding principle, namely that a good choice of the space V is important to flourish the interplay between functional analytic properties down here and properties of the dynamic system up here. And also this we have seen today, very classical and good examples that illustrate well what beautiful things are happening are topological dynamics, where we can look at the space of continuous functions as a choice for our vector space V, and or measure preserving systems, where we look at LP spaces with respect to this invariant measure. And I think also we have seen this refined guiding principle today within action, namely that it's good if we choose our V in such a way that it translates all the properties of our interest to properties of the Koopman semigroup and vice versa, and if possible, even to spectral properties of the Koopman semigroup. And yeah, and this guiding principle I'd like to follow a little bit towards sparsity direction. And therefore we'll focus on the case of continuous or of topological dynamics, and we look at the Koopman operator on a space of continuous functions. So here again, how we define the Koopman operator, and we'll also need the Perron-Frobenius operator. but just because it's very beautiful, I think here I want to state some nice properties of the Koopman operator on the space of continuous functions. Namely, it's well-defined, strongly continuous semigroup, linear, contractive, and non-negativity preserving algebra homomorphism. So it seems like we get everything that we could wish for. And we can also look at the adjoint semigroup, which is called the Perron-Frobenius semigroup, and it acts on measures, and namely by pushing forward a measure by our flow. Here, as a reminder, the push forward measure is defined like this. So we measure how much volume flows into a set. Okay. So since now we have defined what we need for the Koopman operator, we can look at sparsity. So what do I mean by sparsity here? By sparsity, I mean that we can decouple a larger system into several smaller systems. So this has the goal that it's hopefully easier to investigate some properties of the global system by investigating them on the smaller systems, but we shouldn't forget that in the end, we want to put the properties from the smaller system together to the global system to really get back a global property. Okay, and the smaller system structure that we are looking at are factor systems. So I think here I can do some commercial for last year's talks in this session by Nicolas Deco. It was really beautiful, I would say. I don't provide such abstract stuff, but he did something very nice. Okay. And here, so what is a factor system? A factor system of a dynamical system here is a triple of a set together with a semi-flow here, such that this becomes a dynamical system, and a map P, a factor map P, which maps from X, the state space of the original dynamical system, to our set Y, and this map should be surjective, such that we have the following property here. And this just states that this diagram here is commuting. And in other words, it means that the map P sends solutions of the original dynamical system to solutions of our new, hopefully smaller dynamic system. Okay. And these provide our building blocks for what we'll, or sparsity building blocks. Okay. And one easy example. So the simplest example that provides some more or less trivial sparse structure is the following. So we have here a system of ordinary differential equations. So this induces a dynamical system by looking at the flow. But the dynamics here has a very particular form. So we see that the dynamics of the state X only depends on X, but not on the states Y and Z. While the dynamics of the states Y and Z, of the state Y, for example, does not depend on the dynamics or does not depend on the state Z. And similarly for the state Z, the dynamics here does not depend on Y. So that means they behave kind of independently. They're still coupled through this variable X, but still this allows us to formulate the following dynamical systems. So one, we can just project on the X coordinate, and we can treat this as an independent dynamical system. Or a separate dynamical system, independent is not correct. We can also project on the XY coordinates and see this does not depend on Z. So we can do this. And similarly for the X and Z components. So this allows us to take our whole system here and reduce to some smaller systems. We can even here, as I said, we can even draw a third arrow for a third dynamic system. And it still has the property that all in all, we still investigate the states X, Y, and Z as well. So we observe still enough. Okay, and once we have this, now we want to, this basic example, we would like to translate this into Koopman language. So what happens? This here is a well-known result. So a reminder up here what it means to be a factor system is this. And suppose we have such a factor system Y of say we have the two dynamic systems, X and Y. And if we look at the composition operator, AP, induced by such a map, by map P from X to Y, then this composition operator here intertwines the two dynamic systems here. That means we have this relation here, if and only if Y is already a factor system of our system X. This comes very naturally from the functionality of the Koopman operator or the composition operator. But just to see the Koopman procedure in action, let's have a look how this is done. So let's apply the left-hand side here to an arbitrary G, to continuous function on Y. By definition of the operator Kp, this here is nothing else than G composing with P. Now, the Koopman operator also just composes, but with the flow here. So we get this. Using that composition is associative, we can just change brackets to here. Do you see it, by the way, when I point with my mouse? Yes? Okay. And here at that point, we use that we have a factor system, so we can just replace this part, which is the same as here, by this part, which happened here, and now just translate it back to what it means. So here, composing with P is applying the Kp, the composition operator Kp, and this is the same as applying the Koopman operator for our second dynamic system. Okay, so this is very natural, and from this intertwining property here, we also get this also very well-known result about the spectrum or the point spectrum. So assume we have the dynamic system on X and the factor system here on Y, map B, then and with corresponding Koopman semigroups, denoted by T and S for the corresponding dynamic systems, then this allows us to transfer eigenfunctions and eigenmeasures from the factor systems to the whole system, but only one way always. So for eigenfunctions, that means eigenvectors of the Koopman operator, we get the following. If we have an eigenvector of the Koopman operator for the factor system with eigenvalue lambda, that means that we have the following for all t here. Then when we push it with the composition operator, the intertwining operator here, we get an eigenvector of the of the Koopman semigroup for the original system with the same eigenvalue, and for eigenmeasures or eigenvectors of the Perron-Frobenius semigroup, we just get the reverse direction due to having a covariant factor. So that means when we have an eigenvector of the Perron-Frobenius semigroup with eigenvalue lambda, then when we apply the adjoint of the intertwining operator, which means pushing forward by our factor map P, we get an eigenvector of the Perron-Frobenius semigroup for the factor system. Okay, so we only had the one way always, and this really just follows from the intertwining property that we just showed. Okay. So, but here, when we remember our refined guiding principle, it would be nice if it's possible to characterize this sparsity or factor system structure somehow both ways. So here we only said we can go from we only can always go one way. Now we would like to see that in some cases we can even go the other way. So sure. So this is what we've shown. If we have an eigenmeasure here, we can find an eigenmeasure for the factor system, and here it is the other way around. And yeah, we will answer the question when we can draw arrows in the reverse direction partially. And first we will look at invariant measures. So what is this? These are measures that are fixed points of the Perron-Frobenius semigroup. So that means they're invariant under the push forward. And here again, definition of what being pushed forward means. Okay, how would we do this? So we arrive directly at this following basic task here. So the idea was we have a whole system, we decompose it into many smaller systems. On these smaller systems, we want to investigate the dynamical system, maybe find invariant measures there. But then we want to put them together so that we get a global object for our whole dynamical system. So the easiest case, even without considering dynamics, is the following. So suppose we have a set X and we have some maps P from X to some spaces Yi, and we fix some measures Yi on some measures mu I on our spaces Yi. Now, we should ask ourselves, is it possible to put them together corresponding to our factor maps P, such that they're all induced by the same measure that comes from X, namely by pushing forward with the corresponding map Pi. And this can be characterized by the so-called Gluinglemma, which is often used in optimal transport, which says the following. Say we have two probability measures, one on X times Y and one on Y times Z. Then we can find a probability measure on the common product space such that its marginals are exactly nu and gamma, if and only if the original two measures here, they share the same marginal on their common space. And that this point is necessary really just follows from applying here the push forward of the projection, but also nicely I would say is that you can even, based on those two measures, you can directly construct one measure mu that solves this here, which uses the disintegration theorem. But it's quite neat, actually. Okay, and once we have this Gluinglemma here, we only need to add the dynamical part, and we will arrive at the following main theorem. So, but to do so, let's finally fix what we mean by a sparse structure. So as we've seen, it works better with projections. So we restrict our factor maps to be projections. That also means that our space X should have some product structure. And then we say that the dynamical system is sparse if we can find factor systems which are induced by canonical projection maps, such that here they project onto the coordinates indexed by those index sets i's, such that each state is at least contained in one of these factor systems. So that means we can really cover we cover the whole dynamical system. So we observe everything, so to say, by the factor systems. And once we have this, we show the following. Namely, this here is just in a case we have two factor systems, but this can be extended to finitely many factor systems. So suppose our dynamic system is sparse, and we can find here, say, two factor systems with the factor maps being projections, such that every state is covered. And let's fix two invariant measures for our factor systems. Then we can find an invariant measure for our whole system, which has the given two marginals, if and only if the marginals satisfy this necessary condition of having the same marginals on their common components, which we've seen in the Gluinglemma before. And showing this again, the necessity of this part is simple. It just follows from this identity here and applying the push forward. So the more difficult part is to actually find such an invariant measure for the whole system. And to do so, we will apply the Markov-Kakutani fixed point theorem. Why? Because an invariant measure is exactly a fixed point of the Perron-Frobenius semigroup. So what we want to find is a fixed point of the Perron-Frobenius semigroup, which is a probability measure. So it's non-negative and has mass 1. And it satisfies here this marginal constraints. Okay, so that's why it's interesting to look at this set here. And first, we note that this set is non-empty because we can just apply the Gluinglemma. Because the sufficient condition for the Gluinglemma is exactly this condition here. So we know K is non-empty. And further, we only have affine constraints here that come from bounded operators. So that means it's also weak star closed and convex. And it's a subset of the probability measures. So hence, it's also weak star compact. And what remains before applying the Markov-Kakutani theorem is to check that this set K is invariant under the Perron-Frobenius semigroup. So let's check this. So of course, probability measures are preserved by the Perron-Frobenius semigroup. So we just need to look at these affine constraints. And this basically follows from having our factor system structure. So this is what enters here. And then we just need to use covariant functoriality of the push forward. And then we can apply the Markov-Kakutani theorem and get a common fixed point of the Perron-Frobenius operator in the set K, which exactly means we have found an invariant measure with the given margin. Okay. And yeah, in the title, I also talked about sparsity structures of the Koopman operator, but here this is a little bit more difficult. So I would like to have done something for eigenfunctions, so eigenvectors of the Koopman semigroup, but here I am missing compactness properties, so I have to restrict to a much more restrictive setting. And there then something is true. I don't want to go into the technical details here. So for those of you who are familiar with principal eigenfunctions, so we showed that principal eigenfunction also have this decomposition property that they come exactly from subsystems. Okay. But nevertheless, I would like to give an application for the Koopman operator when having sparsity. And so there will be another small data application come here. So what did we do? We looked at a very simple example of a system with a sparse structure. So we looked at the following simple Duffing equations here. And also two other Duffing equations, which are influenced by the first one. So this is very similar to the structure that we've seen before in this introductory example of sparse dynamic system induced by ordinary differential equations. And once we have this, we can look at dynamic mode decomposition, which is what people like to do when they work with the Koopman operator and data. And once if we do this, while we want to exploit that we have the subsystems that consist on projecting on those x1 states and x2 states, or also on the x1 and x3 state, we got the following. So in blue here, this is the exact trajectory that we want to estimate using this dynamic mode decomposition from data. And here in red, this is the dynamic mode decomposition that we get when we run the dynamic mode decomposition for the whole system. And here the orange one, which seems to fit the exact blue one much better than the red one, is the dynamic mode decomposition that was only based on the corresponding subsystem of the state that we want to investigate. So here, at least at this example, we see that using the a priori knowledge that our system has some sparse structures allows us to reduce complexity of some smaller parts by looking at smaller subsystems instead of the whole thing. And in applications, hence we expect to have some better or less frosty results. And by that, I would like to conclude my talk. And thank you a lot for having me here and listening. And if you have questions, I'll try my best to answer them well. Thank you.